Good evening. So we finish this class of developmental artificial intelligence. It is the fourth and last lesson. So the outline, I will begin with presenting our research on robots. So far I've only talked about research in computer science and algorithm, but I'm going to talk about research in robotics, that is designing new kinds of robots. And then I will conclude this course by summarizing the approaches that I introduced during those 3 lessons. And then we will continue the exercises. So research in robotics. So as I explained previously, our approach based on interactions leads us to design robots that are different from existing robots, because we need to think about the possibilities of interactions between the robots and the world. So we develop specific robots different from what we find in commercial robots. So we imagine new ways to design robots that can support our approach based of learning based on interactions. So here with these robots, we aim at reproducing the experiment that I showed you last week with the fishes. So this robot has a visual system. So we use a camera that points towards a spherical mirror to give the robots a panoramic view of its environment. We have a tactile sensor that detects collision in front of the robot, and we have an optic sensor that detects color patched on the floor below the robot. So with these various sensors, we try to reproduce the primitives of interaction that we implemented in the experiment in the simulated environment with the fish. So, for example, the interaction to eat a fish is reproduced by the interaction of moving on a color patch and detecting this color patch with the color sensor beneath the robot. So we can associate a positive value to moving toward a patch and detecting the patch, which will generate the comportment, the behavior of moving towards the corresponding patches. So it's a design in progress. So in the future, probably we will implement a possibility for the robot to go backwards, and we will simultaneously endow it with a sensor to detect collision behind, on the rear. So as we develop smarter algorithms, we need to think of the new possibilities of interactions available to the robot that can show the possibilities, the new possibilities of the algorithms. So in parallel, we develop the algorithms and the robot. So here is a short video of what we are doing with this robot. So you can have more information on the website of my student, Simon Gay. So this video was recorded after the robot had learned to move towards blue patches. So here it moves toward this blue patch. So on the top right is the robot's vision with a low-level algorithm that extract cyan colors in the visual field. And so those low-level algorithms are hard-coded, and our learning mechanisms run on top of those low-level algorithms. Here we introduce walls that hide the blue patch, but on the bottom right area you can see the spatial memory of the robot, and in spite that it does not see the blue patch, it is still present in its spatial memory, so it tends to go toward it and to bypass the walls. So here we study the problems that I introduced last week concerning how to turn around obstacles to reach a desired object. So avoiding obstacles in itself is not that difficult, but the problem is how to design those algorithms that avoid obstacles within the conceptual framework that I presented earlier. That is, by thinking in terms of interactions and ignoring at the beginning that obstacle exists. So the robot has to explore its environment, discover the existence of obstacles that afford negative interaction when they bump into it, so then learn to avoid those obstacles. Yes, so the spatial memory of the robot is similar to the one I presented last week. So it's a short-term memory in an egocentric referential. But here we have additionally implemented a form of repulsion from words. So when it knows that walls afford negative interactions, it tends to move away from them. So that's our current state of research. So hopefully in a year or next year, maybe we'll have more to show. Okay, so as a conclusion of this course, I'm going to situate this work within the general framework of artificial intelligence. So first, there is a first line of demarcation in the area of AI. It is the demarcation between symbolic and non-symbolic artificial intelligence. So below this line is symbolic AI, which is focused on problem solving and are based on the notion of physical symbol proposed by Alan Newell in the 60s. So you can see symbolic AI as if all elements of the world had a label, and the designer of the system put this label on each element. So it's a little bit like this orientation table where every element of the world has a label, and then the environment passes this label as a symbol to represent the element of the world. So, for example, the environment can pass a symbol apple, and then the designer of the agent encodes a semantics for these symbols. So, for example, there are symbols fruit and edible objects. And the designer encodes a rule such as An apple is a kind of fruit, and the fruit is a kind of edible object. So when the agent receives an apple, it says, okay, so it's fruit, so it's a kind of edible object, so I can perform the action eat. So we implement a reasoning engine to process those rules. So that's the origins of AI. Most of the success of AI that we know are based on these principles. So for example, a program that plays chess implements these principles, so it receives as an input the position of the pawns, pieces on the chessboard, and then it knows the rules for playing chess, so it simulates those rules to make a decision. But that's not what we are doing here, because the problem with that is that it presupposes that all the world has been labeled by the designer. And if we want to design robots that interact with the real world, we cannot a priori label all the elements of the world. So we want to design a system that learns by itself to categorize objects in the world and to learn what the world is made of. So it's very crucial to understand the difference between symbolic AI and non-symbolic approaches. So with the symbolic AI, for example, you can design automatic translation algorithms. So you encode the semantics of words, and you create a system that can translate. But of course, you know well the limits of this approach. So if you have ever tried an automatic translation system, you see well that it does not rest upon the meaning of words, but only apply rules to translate. So in the context of non-symbolic AI, there is another demarcation line. So this one is much less consensual, and it's less clear in the domain of AI. So it has been labeled situated cognition, for example, by Clancy, 1992. So below this line, we have what we could call disembodied learning, in which the agent doesn't need to be confronted to its environment. It's a passive observer of the environment. So most of the research currently in non-symbolic AI is below this line. So below this line, there is a kind of naive confusion between the input data of the agent and perception. It is considered that the input data represents the world and can be understood as a perception of the world. So they begin with this hypothesis, and they design algorithms that exploit this hypothesis to construct knowledge about the world. But above this line, we don't consider the input data as the perception of the agent. Here is this quote from Clancy, that perception and action arise together dialectically from each other. So we really start with interactions to construct a perception of the world and knowledge of the world. So in this case, perception of the environment is an internal construct in the agent, but it's not the data that is received as input. So this demarcation is what we call the difference between learning by registering and learning by experiencing. So the traditional approach, the data comes from the environment to the agent, and then the agent performs an action in the environment. But in our case, we begin with the agent. The agent performs an experiment in the environment, and the input data is a result of this experiment. So in our case, in a certain state of the world, the agent may have one experience that will return an input true, for example, but it can have another experience that would return the result false in the same state of the world. So that means that the input data does not correlate with the state of the world. So all the theoretical discussion that I presented in the first lesson, they explain this distinction at the theoretical level. But the advantage of the modeling approach that I have presented in this course is that it specifies formally this difference. So below this line we have many. So in this case we don't pass labels to the agent, but the environment still passes what we call an observation, that is a code that is a function of the state of the world. So we did not encode the meaning of those codes, so it's not symbolic AI, but still the relation state observation is assumed to be surjection statistically. That is, a given state of the world will statistically always return the same observation. And so we implement algorithms that assume that a given state of the world induces a given observation, even though it's partial and subject to noise. So that's what we don't want to do, assuming that the code received from the environment represents the environment. So we are above this demarcation line. So above this line, there are a lot of theoretical studies that argue that we should situate ourselves above this line. So, for example, in the domain of philosophy, people refer to theory of phenomenology, Heidegger, and in robotics, some authors have suggested to inverse the perception-action cycle, as we do. There are also the notion of sensory-motor contingency theory proposed by O'Regan and Noé. Which suggests that the goal of the agent will not be of reaching a predefined state of the world, but to master the laws of sensory-motor contingencies. On the implementation level, I can cite a few work. So there is the Horde architecture by Sutton and co-authors on all the domain of cybernetic control theory. This is the domain about asservicement, proportional, derivative, integral systems. This is a quite old approach in which the input of the agent is not a direct representation of the state of the world. However, those old approaches do not permit to generate self-programming in the system, as we do. So here, we situate ourselves here at this level with the radical interactionisms that I introduced. And here I represent the validation paradigm. As I said, we are not going to implement agents that seek to reach a predefined goal, but we will assess our algorithms through behavioral analysis. So by visualizing the traces of behavior of the agent, we can show that smart behavior emerge. So this relates to the theoretical works on Oregon and Noé about sensory motor contingency mastery, and also the work of intrinsic motivation by Pierre-Yves Houdeillet in France, in Bordeaux. So this gives an overview of developmental learning within the general field of AI. So you can situate it within the literature in AI. So if you are not convinced that the perception is not input data, there are many experiments that illustrate that are called change blindness. So in this example, you see those spots blinking, and after each blinking, there's something big in the picture that appears and disappears. Can you see it? So yes, this is this bag on the table. So that illustrates the fact that we are not only processing the data that comes into our head. If we did, we would see this immediately, but we don't. We perform a dynamic exploration of the scene, and because we are disturbed by those spots here during this exploration, we don't see what changes. So you can see more examples of such experiments on this website, and if you search on YouTube, change blindness, and so on, you will see many examples, funny examples. C'est ce qui nous incite donc à raisonner autrement dans nos algorithmes d'apprentissage et dire finalement. So this suggests to think differently when we design learning algorithms. So in our case, we implement experiences of interaction of the agent with the environment that returns input data, but the input data does not directly represent the world. And then the problem is to find regularities in sequences of experience, as I said before. So this is a theoretical justification of what I presented you earlier. So in this case, the environment does not pass an observation to the agent, but a result of an experiment initiated by the agent. The problem is that this vision is counterintuitive. So it is difficult to imagine what is the input data because it does not represent the environment. And we don't implement agents that reach a predefined goal, but only that learn to master the regularities in the experience of interaction. So here I made this slide to insist on the counterintuitiveness of this approach. So it is a little bit as the counterintuitivity of the revolution of Earth around the Sun. As we know since Copernicus, intuitively we observe that the Sun seems to revolve around the Earth, but we know that it is the opposite. But it is difficult to deal with this counterintuitiveness when we think and talk in our everyday life. So we still say, I'm going to watch the sunset or the sunrise. So intuitively we tend to follow our intuition, even though we know that there is a counterintuitive reality that explains things better. So here it's a bit the same. We have the intuition that we receive input data about the state of the world, but this is a false impression. And in fact, all the theory of psychology and theory of knowledge tells us that this is a false impression. So we are totally conform with the main streams of philosophical theories that support this idea. So we fit the framework of the theory of knowledge that we had for at least 3 centuries in the Western world. However, surprisingly, all the traditional AI seems to ignore this idea. And so we position ourselves against the field of traditional AI because we endorse this counterintuitiveness. And all the difficulty is how to think about how to design our agent with this in conformity with this counterintuitiveness, even though we cannot really think about it. So it took about 500 years for these counterintuitive ideas of Copernicus to spread in the general public. So maybe it will take a little while for these counterintuitive ideas of cognition to become familiar to most of us too. But if we manage to overcome this difficulty, that will allow us to implement a level of artificial intelligence that is intermediary between a low level that we can call stimulus response adaptation and a higher level that we call reasoning and language. This intermediate level, we call it semantic cognition, and intuitively it would correspond to the intelligence of animals. So animals don't talk, and they don't follow complex reasoning, but they generate behaviors that are not trivial, that are more complex than simple stimulus response adaptation. So that's the kind of behavior that we seek to achieve. So at this lower level, we have traditional reinforcement learning, traditional method using neural networks used in machine learning. At the top level, we have rule-based system, ontologies, traditional AI. And at this intermediary level, we have the level of knowledge grounding, how knowledge can be grounded in experience of interaction, which leads to sense making, and with the crucial aspect of self-programming, as I introduced. So as takeaway ideas, most important ideas, the most important is probably to think in terms of interactions rather than separating perception and action, to think in terms of generated behaviors rather than aiming at learning data. So data is not the goal in itself. The goal is to organize behaviors. So of course, generate intelligent behaviors raises many questions. What is, how to define an intelligent behavior? So there is currently no consensus within the research community in this domain for agreeing on what we can consider an intelligent behavior or not. So the work that I presented here contributes to specify the kind of behaviors that we seek to achieve. We need to define more specific criteria that we seek to use to assess our agents. And of course, you should keep your critical thinking and continue inventing new approaches. So we have this hard problem of AI, which is to generate sense making. And you can imagine different formalization. So the traditional formalization is to think in terms of observation. The formalization that I introduced here is to think in terms of interaction and experience and results, but that's probably not the ultimate model. Probably other models still remain to be invented. And that's a good news for you who are students, because this problem will not be solved before you graduate. So there are still many things to invent. Okay, so the final exercise. So I'm going to show you traces that we can obtain with Agent 3 in Environment 3 that we developed last week. So as I said, the Environment 3 behaves like Environment 0 at the beginning and then switches to behaving like Environment 1. And so the agent has to first adapt to the first environment and then readapt. So here the switch occurs after step 5 and step 10. So after step 10, it turns back to environment 0. So here's the trace. So steps 0 to 4 in environment 0. So it performs E1 and receives R1. It performs again E1 and receives R1, which is negative again. And it learns E1, R1, E1, R1. And then because it is in the context of E1, R1, it activated E1, R1, E1, R1 that it just learned, which tells it that if it does again R1, it would likely receive R1, which is negative. So it proposes E1 negatively. So it changes, so it chooses E2 and receives R2. So the agent is happy because it's positive. And now it learns E1, R1, E2, R2. So it continues choosing E2, then it learns E2, R2, E2, R2, which activates again E2, R2, E2, R2. So it received E2, and then it changes again. So it does E2 receives R1, which is negative. So it learns E2, R2, E2, R1. So no behavior is proposed here, so it continues with E2. So it learns that in the context of E2, R1, it receives E2, R1 again, which activated E2, R1, E2, R1, which proposes E2 with the negative values. So because E2 is proposed with a negative weight, it switches to E1 and receives R2 and learns E2, R1, E1, R2. And so it stabilizes with E1 to receive positive value. And then on step 10, it changes again. So it does E1, it receives R1, which is negative. It learns E1, R2, E1, R1. And so it is contradictory with what it learns previously. So there are two activated interactions. One in the context of E1, R1, it did E2 and receives R2. And the other one, in the same context, it did E1 and received R1. In this case, those are coherent because E2 is proposed with a positive value and E1 is proposed with a negative value. So here we sort those propositions from the highest to the lowest. It takes the highest, so it's E2. It obtains R2, which is positive, so it is happy. So again, it activates previous experience, E2, R2, E2, R1, and E2, R2, E2, R2. So here there is a contradiction. Once, when I did E2, I had a negative result, and the other time when I did E2 in the same context, I had a positive result. So what do? This is where the weight of activated interactions matters. So how many times did I receive R1 in this context, and how many times did I receive R2 in this context? So because the weight is higher, it is more likely that when I do E2, I receive R2, so positive. So I choose E2 and receives indeed R2, which is positive, so I'm happy. So we see the importance of the weight of activated interactions that allows the agent to select the most probable, so the experience that will give the most probable result. So as I said, in the same context, several interactions are activated. So the agent has to choose among the proposed interactions to execute the best. So we'll stop here with the agent. We are not going to implement an agent 4, but we are going to implement Environment 4 just to show you what we would like to do to go beyond Agent 3 in the future. So environment 4 returns R2 only after twice the same experience. So it makes E1, receives R1, it makes E1 again, receives R2. And then if it continues choosing E1, it will always receive R1. So it has to choose E2, but the first time it's negative, so it has to do twice E2 to receive R2. And if it continues doing E2, it receives R1 again. So it has to alternate E1, R1, E1, R2, and then alternate E2, R1, E2, R2, and so on. So it will always have to enact a negative interaction to be able to enact a positive interaction. So the agent 3 will not be able to find a solution in this environment because the choice depends on the two subsequent interactions. So the temporal dependency has been increased to 2 steps. So the choice to be made depends on the 2 following steps. So it will have to anticipate 2 steps ahead to make the right decision. Additionally, it would help it if it based its choice on a context that goes 2 steps backward. So here's the code for the environment. So if experience at t minus 2 differs from the experience at t and experience at t minus 1 equals experience at t, then results equals R2, else results equal R1. And then I would like you to please write a report which will have this structure. So first, agent 1 explain how you implemented the code and gives traces of agent 1 in environment 0 and 1 with various motivations and explain the agent's behavior. The same for agent 2, explain the code, trace in environment 0 to 2 with different motivations, and please explain the behavior of the agent. Similar with the agent 3, in environments 0, 1, 2, 3, and then in the environment 4, it will not be able to find the optimal behavior. So again, please explain why, and as a conclusion, please explain what will be the next step towards designing agent 4 able to adapt to environment 1 to 4. Non, vous me faites un petit paragraphe pour expliquer. Alors je ne vous demande pas d'en écrire des tartines. Votre temps est précieux, le mien aussi. Donc inutile d'élaborer. Mais bon, si vous me mettez un petit paragraphe qui explique le code, comment il marche, ouais, c'est ce que je vous demande. Un paragraphe pour expliquer le code et un paragraphe pour expliquer les traces à chaque fois. C'est bon? Très bien. Bah, rendez-vous en salle de TP6, TP7.